thank you for the intro. My name is Nico, and I'm going to talk about database replication for web applications. Let me illustrate, I'm missing a slide. So web applications are increasingly built using service-oriented architectures. Those components are loosely coupled and can be deployed independently and scaled up independently. Let me illustrate this with a simple example featuring an e-commerce application. So we have our store front end, and we'd like to augment our store front end with some features. We'd like to add a product recommendation feature and do some analytics on the platform. So we instantiate two services that are responsible for those features. Each component uses some common subset of the data. For example, both the front end and the recommendation service would use pieces of the user data and the product data. So this data is stored in different databases. The database is picked depending on what the service needs to accomplish. We might want to use a graph database to power our recommendation service, like Neo4j. And similarly, we might want to use Elasticsearch to power our analytics service, because Elasticsearch is really, really performant when it comes to do aggregations and analytics. And to generalize, each component in the ecosystem of the application represents different facets of some common subset of data. This data is stored in the most appropriate database for the task at hand. So this leads us directly to the problem we're solving. How do we synchronize the data across all these different databases? So we want to do database replication with the following requirements. Our replication system should be compatible with a vast amount of databases. It should be easy to use. Orchestrating the data flows inside the internal ecosystem should be seamless for developers. It should provide good consistency semantics at scale. And the replication mechanism should be failure tolerant. Specifically, network partition should not result in having half of the databases missing some data. So what are people doing right now to address the problem of database replication? We've looked at the latest work in academia and in the industry, and they fall into the following categories. First, we have same database replication. There's a ton of work in this area, mainly to address availability and scalability concerns. These systems are not useful for us as we want to do cross-database replication. Then there are some cross-database replication systems that tell the transaction log of the source database. Parsing the proprietary binary format of the transaction log is brittle and hardly generalizable. An example of such system is LinkedIn Databus that parses the Oracle DB's commit log. Then there are systems that do database federations. These systems aim at making a bunch of databases appear as a single database through a single API. Depending on the query that needs to be executed, the system should pick the right database to perform the query. It's actually hard to leverage the full feature set of each database through a single abstraction. So it's pretty limited. And then there are manual solutions that leverage existing publisher-subscriber infrastructures. Sadly, this is hard for developers to get right. Specifically, fault tolerance is often missed and consistency semantics are poor. We present Synapse, the first system that solved the database replication problem with all the requirements that we need, namely, compatible with many databases, ease of use, good consistency semantics at scale, and failure tolerance. We'll solve this problem specifically in the context of web applications. And our key insight is simple. Instead of operating at the database level, like most of the previous approaches, we operate at the application level. And by operating at a much higher level of abstraction, we're able to fulfill our desired guarantees with little effort by leveraging the semantics of traditional web applications. Typically, web applications are structured following the MVC pattern. MVC means Model View Controller. It's a way of separating concerns. The browser sends an HTTP request to the controller, and the controller accesses data from the models, and then renders a response back to the browser with views. Each language has its sets of popular MVC frameworks. With Ruby, you can use Ruby on Rails. If you like Python, you can use Django. And if you do some C#, there's ASP.NET MVC. So let's look at the models. Models are built on top of object relational mappers, ORMs. The ORM does the heavy lifting of interacting with the database, so developers don't have to write database queries. An example of model is the user model. The user class will be mapped to the database table user. User object will correspond to database rows. The application stack actually looks like this. At the bottom, we have the database. Then above it, we have the ORM, then the models, and then the controllers and the views. Over the years, many ORMs have been developed, each one targeting a different database. These ORMs have similar APIs. For example, regardless of the combination of ORM database, you can expect to just be able to call user.create and it would work with any database. Here I'm showing what a SQL ORM would do when receiving a user.create query. It would generate the appropriate SQL code to insert a new user in the users table. Synapse interposes on the ORM to monitor accesses to data objects. This allows Synapse to replicate data from one database to another without developer intervention. And with this unified data layer, Synapse is compatible with many databases, including Postgres, MySQL, Oracle, MongoDB, TokuMX, Cassandra, Elasticsearch, Neo4j, and EverythingDB. In most cases, Synapse seamlessly translates data models between databases, but in some cases, it might not be so straightforward. So Synapse provides lightweight abstractions to developers to specify translation layers easily. You can find more details in the paper. And so that's how Synapse translates data from one database to another without having to deal with the intricacy of each database. So how does this work under the cover? Suppose we have two MVC applications, a publisher and a subscriber. We want the publisher to export some data, which a subscriber imports. So the first step is, during runtime, we monitor object accesses on the publisher side. Any modifications made to a published object triggers the replication mechanism. To generate the message payload to be sent to the subscribers, we call the getters methods on that object, on the object that just changed, to get all the published attribute values. For example, with a user object, we would call the name and email getters and put those values in the payload. Once prepared, the payload is published to the message broker. The message broker persists these payloads in message queues and distributes the payloads to the appropriate subscribers. Synapse relies on existing published subscribe systems, such as RabbitMQ or Kafka. Once the subscriber receives the payload, it processes the payload by instantiating the appropriate model, setting the attributes through the setters methods, calling save, and finally adds the payload to the message broker. So to summarize, we replicate objects from publishers to subscribers. And the data translation is done by calling getters and setters on each side. All of this is done transparently without the intervention of the developer, aside from specifying what gets to be published and subscribed. So how does the developer specify what gets to be published and subscribed? Let me introduce you to the Synapse API. Suppose you have a user model written in the Ruby language. So here we're using the MongoDB ORM, which is a MongoDB or ORM for Ruby. There's two fields declared, email and name. So to publish the user model, all we need to do is wrap the fields that we want to export with the publish keyword as such. This is exactly what a developer would do to export the user model. This is not pseudocode, this is real code. So now let's say that we want to import the data in a separate service running on a SQL database. Here we are using the Active Record ORM, which is a standard SQL ORM for Ruby. Similarly to the publish API, we use a subscribe API and wrap the attribute that we want to import. And that's it. So Synapse is really super easy to use. Developers use the publish and subscribe keywords directly in their model, and Synapse handles the rest. And even though the Synapse API is very simple, with just two keywords, publish and subscribe, one can construct complex ecosystems of services. And I will show two examples. The first example is how to do data model mashups. Suppose you have the main application publishing a user model. Now say we have a moderation service that subscribes to the user model and detects suspicious users by doing some machine learning. The service can then publish a new attribute, is suspicious, on the subscribed user model. Finally, a third service can then subscribe to both sources of the user model to get an aggregate view of the user model. This way, developers can use the publish and subscribe keyword to do mashups of models in an intuitive manner. The second example is how to implement asynchronous triggers. For example, suppose you want to implement a service that sends a welcome email whenever a new user registers. One can simply subscribe to the user model and add an ORM provided callback before create that triggers an email. This is intuitive to developers as they are already familiar with this ORM provided callback API. So far we've seen that Synapse provides a foundation to share data among independent services in a clean manner with a very simple API that can be used for various use cases. namely database replication, data model mashups, and asynchronous triggers. But doing it at scale brings another problem, consistency. I'm going to illustrate the consistency issue with an example. Suppose you have two services, a publisher implementing a document sharing platform and a subscriber sending emails. When a user uploads a new document on the platform, we want to email that document to his friends. Consider the following scenario. A C-level executive comes back from his company's quarterly meetings and proceeds to make some radical changes. He's going to use the document sharing platform to share his new plan. But before doing so, he carefully removes an employee from his friends list and only then upload a very confidential document. So what happens under the cover? The publisher is going to broadcast two different data updates to the subscriber. The first one being the removal of the soon-to-be-fired employee, and then the creation of the confidential document. At scale, with a proper synchronization, the two data updates may be processed in the wrong order. This will result in sending the confidential document to the wrongfully funded employee. So here, see, like this bug is very vicious because the developer won't catch it. No exceptions are thrown, no database constraints are violated. This bug instead manifests into a lawsuit, which is undesirable. So what do we do? Intuitively, we want to parallelize the workload as much as possible, while serializing what needs to be serialized. So how do we know what needs to be serialized? We cannot rely on developers to tell us because they will make mistakes. We cannot rely on static data relationships, like foreign keys declarations in models. That would not be good enough. Instead, Synapse dynamically discovers data dependencies at runtime. And it does so by leveraging the controller abstractions of the MVC framework. The controller is the entity that processes HTTP requests and interact with models. Synapse monitor model accesses within controllers. And so Synapse provides three useful guarantees. First one is all the writes within a controller are serialized. This ordering is enforced on subscribers, and this is to match developers' expectations. Second, all the writes within a user session are serialized. This is to match users' expectation. And finally, any given write is marked to have causal dependencies on the previously read objects within the controller. And the reason why this is useful is because controllers are stateless. Any data that is important for a write will be read through the database during the controller execution. And so when a subscriber processes an object update, it can read other related objects and their state will be coherent. So to summarize, we try to give the subscriber the illusion that it's running on the publisher database. These semantics allow developers to drastically simplify their code base because they no longer have to take into account those weird corner cases of out-of-order updates. Developers think in a single-threaded mindset, while their application is massively parallelized. Synapse implements those consistency semantics by transparently intercepting all read and write queries to the database, inferring accessed objects, and versioning them. The objects' versions are stored in a separate version store per service. In our implementation, we use Redis. And finally, Synapse is fault tolerant. In a nutshell, Synapse do two-phase commits all the way from the publisher to the subscriber. On the publisher, the tricky part is to do three things atomically. First, we need to perform the database, the write to the database. We need to update the object version, and we need to publish the message to the message broker. And those three things need to be done atomically. And we do all this with two-phase commits. To summarize, we have a framework to share data in a clean manner to do cross-database replication that is easy to use, with good consistency at scale, and is fault-tolerant. We implemented Synapse on Ruby on Rails in 4,000 lines of Ruby. Synapse currently supports 9 databases. We implemented more features besides what I talked about. For example, we provide a comprehensive testing framework so developers can write integration tests of their publishers and subscribers. Let me show you what can be done with Synapse by showcasing a company that has been using Synapse for the past 2 years. CrowdTap is an online marketing service company contracted by major brands such as Verizon, AT&T, Sony, and MasterCard. CrowdTap has grown rapidly since its inception, and by now has seen over 450,000 users. The platform allows brands to target a specific demographic among CrowdTap users, and give them stuff to do. For example, brands can ask users to answer polls or try out some new products. And the user will be rewarded points, and that will be usable on an e-commerce store. In its early days, because of their rapid growth, they had to extract some features into separate services to keep things under control. They had two services aside from their core application: a targeting service responsible to match users and brand actions, and an e-commerce platform where users could redeem their points. They were synchronizing data across services via a synchronous API, which was problematic as it suffered from performance issues and data inconsistencies due to lack of failure isolation and fault tolerance. To address these issues, they rolled out Synapse in production. Not only the performance and data inconsistencies issues were addressed, but the targeting engine went from 1,500 lines of code to 500 lines of code due to code simplification. Quickly after that, a junior engineer extracted the mailer functionality from the core application. This required the sharing of 24 models. This would have been very difficult to do manually. And because they were so pleased with Synapse, they went on and extracted other major features into separate services. Synapse coordinates 53 data models within their ecosystem. Let me tell you two stories around the reporting and analytics service that show how Synapse allowed the CRAD-tab development team to be more agile. Synapse allows the team to try a new idea very easily. An employee developed a prototype of the reporting service during a hackathon using real-time production data on his laptop. Because of the isolation guarantees Synapse provide, he was able to consume fresh production data without impacting the main application. The business team was able to use it right away, and the reporting has been deployed in production ever since. The second story is about a live database switch done on the analytics service. Normally, to switch database engine on a running service, you would have to wait for off hours, take it offline, migrate the data from the old database to the new one, deploy the new code, and hope for the best. The development team actually used Synapse to do live database switch, a use case we never imagined before. The way it works is that you deploy two versions of the same service, one running with the old database and one running with the new database. Once everything looks good, you redirect all the traffic to the new version of the service and kill the old one. And so this is how Synapse allowed the team to migrate the analytics service from MongoDB to Elasticsearch without taking any downtime. To generalize, Synapse allows development team to be more agile. It lets developers try out new ideas with no commitments. It also let the team manage their services in a very efficient manner. These use cases are common among many startups and medium-scale companies. All right, so let's look at some numbers now. To evaluate the overhead of Synapse, we instrumented the production application of CRAD-tab during a 24-hour window. On average, Synapse adds 8% of additional latency on HTTP endpoints, and this overhead is not perceivable by end users. We were also interested in looking at what would the dependencies look like in practice. So we instrumented the production application to render a dependency graph. This is how it looks. It looks like a hot mess. Each node represents a database update with edges as dependencies. Synapse is responsible to transparently discover those dependencies with minimal overhead on the publishers and apply those updates in the correct order on the subscribers in real time. This image is actually a zoomed-in portion of the bigger picture. When we zoom out, it looks like this. And this is only 2 minutes of real traffic, going roughly at 50 updates a second. But with real traffic, we could not push Synapse to it in its limits. So to evaluate the scaling properties of Synapse, we deployed Synapse on 1,000 servers on Amazon. We deployed 400 publisher machines, 400 subscriber machines, 50 Redis servers on each side to do the dependency tracking, and 100 RabbitMQ servers to move data from publisher to subscribers. We measured the throughput of the system and saw that Synapse scales linearly and reached 60,000 updates per second. As a comparison point, on Twitter, there's an average of 10,000 tweets per second. So Synapse scales well even for large workloads. During our experiment, we also run the publishers and subscribers on different database engines and saw that Synapse was never a bottleneck. To conclude, Synapse does cross-database replication with a vast number of databases. It's easy to use, it provides good consistency guarantees at scale, and it's fault tolerant. We've open sourced Synapse, and you can grab the sources on GitHub. Thank you.
set of subscribers dynamically as the system is running, or whether you have to take it down? Because that seems to be like kind of complicated to be running the two-phase could be protocol between the publisher and the subscribers when the set of subscribers can be changed for a given piece of data.
So if I understand correctly, your question is, can we bring new subscribers and remove some of them during runtime? Absolutely. So the publishers have no, they don't know the subscriber exists. They're completely isolated from subscribers. So when we bring new subscribers, the publishers are absolutely not impacted by their presence. And similarly, when we take out subscribers, publishers don't know about this. However, when we deploy subscribers and publishers, we have to be careful in the order we deploy them. For example, we need to publish, say you want to publish a new piece of data usable for a subscriber, you would publish the publisher first, deploy the publisher first, and then subscriber in that order.
Hi, Mark Shapiro from INRIA. I noticed that all the examples you gave are, they use an acyclic graph, right? So can this be extended to something with cycles or with multi-master replication?
So, so the question is, can we have cyclic graphs in the ecosystem of services, and can we have multi-masters? So in Synapse, we don't do multi-master. We don't want to deal with conflicts. And so we have the concept of ownership. Publishers own the attributes they publish, and nobody else can modify them. So we don't do multi-master updates.
All right. Okay.
So the simple question, maybe I missed that in the talk, is it only synchronous replication that you do, or can you do sync and async? Because you mentioned the reporting use case there, and I suppose reporting doesn't need really synchronous.
Is your question is Synapse an asynchronous or asynchronous replication protocol?
I got the impression it is synchronous from the presentation, or maybe that's wrong.
Oh, it's asynchronous. So the message broker in the middle of the system actually has a bunch of message queues, one per subscriber. And so he will buffer messages coming in, right? And so the subscriber will eventually process these messages, making it asynchronous.
Then do you have a sort of guarantee of what's the latency between replica and...
We don't have any guarantees. However, we measure that it's well under a second. And as I said before, the publisher don't know anything about the subscriber, so they wouldn't wait for the subscriber to do anything, right?
All right. Any other question? Okay, so if that is not the case, thank you.